In this lesson, we're going to be talking about how moving charges create magnetic fields. And this is the first part of electromagnetism. So when charges are moving in a wire or moving in space, they can create a magnetic field. Okay, so that the other way we can create magnetic fields is from moving charges, which is why we sometimes call this electromagnetism, because we're going to be talking about it in terms of charges, which is building up from there. So moving charges, when charges moves, they can also create magnetic fields, and this is why we use that term electromagnetism. So the most common scenario we're going to talk about is if we have a very long current carrying wire. So we have a long wire. Okay, and imagine there's a loop. Obviously, current can't just like go in one straight line forever, but just imagine that it's a huge, really long loop. So there's current, let's say there's current that there's flowing in here, like in a circuit, right? You're gonna have a long, like power lines are a good example of this. You have a long wire, it's carrying current. Guess what? It creates magnetic fields. That's why people say they don't want to live under power lines or near power lines because of the magnetic fields. That's because moving charges create magnetic fields. So if you have a long current carrying wire, the magnitude of the magnetic field is given by this equation. Okay, and let's go through all the variables. So B is the magnetic field, measured in Teslas. Mu naught is a constant. It's called the magnetic permeability of free space. Okay, so magnetic permeability generally refers to like how easily something is magnetized, and free space means like in a vacuum. So this is the magnetic permeability in a vacuum. In AP Physics 2 and even AP Physics C, I don't think we're not going to spend any time too much talking about objects that have different magnetic permeability. We're mostly going to be using this in the context of space, air. But if like you're talking about in water or in iron or things like that, the magnetic permeability can be different based on the material. But for the most part, we're talking about air or like a vacuum, basically. It's a constant. It's equal to 4 pi times 10 to the negative 7. Okay, I is the current in the wire and R is the distance from the wire. So this is the equation of the magnitude. Now, the direction is really important because magnetic fields are directional. So what does the direction look like? Well, if I have a long wire, it turns out there are a bunch of, the magnetic field is concentric circles that go around it. Remember, magnetic fields have to occur in a loop. And so what ends up happening is you have a current flowing in a direction and you have these magnetic field lines that go around it in concentric circles. Now, what's the direction? Okay. Because it's a vector, right? We care about the magnitude and the direction. We use a right-hand rule, okay? And this right-hand rule is your thumb points in the direction of the current. So in this case, if the current's going up, then you have to use your right hand. That's what's called a right-hand rule. You use your fingers will curl in circles around it. So they're just telling you the direction that it's going to curl in there, in that portion there, right? So it's going to curl around in that direction. And that's the direction of the concentric circles. Now, it is weaker as you get further away, because remember the equation is over 2 pi r, so the further away you are, the weaker the magnetic field is. But it's equal to, that's the equation, and this is how you do the direction. So use the right hand, thumbs the direction of the current, and your fingers curl in the direction of the magnetic field, okay? And it makes those circles there. So that's how you get the direction. This is how you get the magnitude here. So let's do some examples of calculating, because remember, magnetic fields are vectors. So we have two long parallel wires shown in the accompanying figure carrying currents in the same direction. If I1 is 10 amps and I2 is 20 amps, what is the magnetic field at point B? So each wire is going to create a magnetic field. Now, if my thumb is pointing down, then the magnetic, like the current's going down, my thumb points downward, my fingers are going to curl in a circle that goes into the screen and out of the screen like this. So this takes a lot of visualization because it's three-dimensional. So the magnetic field is going to do something like this around the front. It's going to go into here and then come around back on this side and then come out. Now, one of the things we talk about for into and out of the page, we will use a dot for something that's coming out of the page or out of the screen, and an X to indicate it's going into the page. And that's because it's like an arrow, right? So if you look at the front of an arrow, right, you see the sharp point. Like, let's use my pen as an example, or we use like a pencil like this. Let me switch to the camera, we'll kind of see a little bit better. So this point is like it's coming towards you, and the back end you think of as like a tail, like an arrow, like the feathers on an arrow, like an arrow, like a bow and arrow kind of thing. Like we use an X to say that the vector's pointing away from you. Okay, so that's kind of how that works, right? That's the idea. So we use a dot to indicate it's coming into the page or out of the page. So this guy's creating a magnetic field. It's going to come out of the page at this point, and the magnetic field from this guy, okay, from this left wire, is going to be mu naught I1 over 2 pi r, which is going to be mu naught times 10 over 2 pi times the distance from there to there. Put it in meters, 0.15 meters. Okay, now let's look at the second one. This guy, I2, he's also creating a magnetic field, and his magnetic field is going to go like this. Come out of, sorry, it's still pointing down. So over the front, it's going to go from left to right. So it's going to come, that's the direction of the concentric circle. And then it's going to go into the page there, and then out of the page here, right? It's the same direction as this one. So this one's going to be pointing into the page. So this B2 is going to be into the page at this point, and it's again mu naught I2 over 2 pi r, which is mu naught times the current 20 divided by 2 pi. And the distance from the wire to that point is 5 centimeters or 0.05. Okay, now in terms of the total magnitude, right, it's a vector, so you got to treat which way is positive. We'll say maybe into the page is positive, like we'll say into the page is the positive direction. So when we compute the magnetic field total, it's going to be B2 is positive and B1 is negative because B1's coming out of the page. They're opposite directions, right? One's out of the page, one's into the page, so obviously they're going to have to be different signs like we add vectors. So this is going to be mu naught times 20 divided by 2 pi times 0.05 minus mu naught times 10 over 2 pi times 0.15. Again, you got to think of them as vectors. Magnetic fields are vectors. They have direction. So we're going to do, just doing the calculations here, and we get 6.67 times 10 to the negative 1, 2, 3, 4, negative 5 Tesla. Okay, like that. Just use the plugging into the calculator. Again, for mu naught, I'm doing 4 pi times 10 to the negative 7. Okay, let's look at another example. So I have a accompanying figure shows 2 long straight wires. They're parallel. Both wires carrying current I in the same direction. What is the magnetic field at P1 and P2? Okay, so let's do P1 first. So this guy, got my thumb to the left, the fingers, so my fingers are gonna curl in front of me and they're gonna go downward because my fingers are curling downward. So it's gonna go down and into the page and out of the page back towards me and then down. So it's gonna go down in front here, then into the page. So it's gonna go this way and then out of the page like that. That's going to be B1, and that's going to be mu naught I over 2 pi r, which is mu naught I over 2 pi times A. The distance is A. Okay? Let's look at this guy right here. So he's going to have so again, going left to right, on the back side it's going up, on the front side closer to me it's going down. So it's going down here into the page, come out and out of the page. So this one's coming out of the page, okay, which is mu naught I over 2 pi A. Now, because one's going into the page, one's coming out of the page, total magnetic field's going to be 0. Because, you see, the blue one's going into the page, so it's an arrow pointing in that direction. This one's coming out of the page. They have the same magnitude. So the magnetic field at P1 is just going to be B1 minus B2, depending on which way you say is positive, and that's going to be 0 Tesla. Now let's do it for P2. Well, P2, it's going to be going into the page. You just draw a bigger circle, right? It goes into the page here. And then for the green one, also going into the page, right? Because they're both, again, down in front. Because for this blue one, right, for the top wire, it's going to be more like this instead, right? And so it's going to go into the page. And then the green one, similar, going to go into the page. So now they're going to add at P2. And the B1's going to be mu naught I over 2 pi. And what's the distance? What's the radius of this circle? The distance from there to there is A plus 2A. That's 4A. And then for the green one here, right, this is a bottom wire, is going to be mu naught I. And what's the distance from this wire to here is going to be just 2A. 2 pi times 2A. Right? And so you can factor out a mu naught I over 4 pi maybe. And then here you'll have 1 over, or 4 pi A, you'll have 1/2. Yeah, because that'll be 8. And then this will be 1 over 1. So it's going to be 3/2 mu naught I over 4 pi a. However you want to simplify it is fine. Just like that. Let's do another example. Circuit with a current has 2 long wires carrying current in opposite direction. So that we have I, it's coming out of the page. See, it's a dot, so it's coming out of the page towards me, whereas this is an X going into the page. Let's see, find the magnetic field at point P near these wires at a distance 1 wire B. Okay, so here, this guy, because he's coming towards me, so I put my right hand out, thumb is towards me because that's the direction of the current, and then it looks like it's a counterclockwise loop, right? So it's going to be a counterclockwise like this, and it's going to have some direction here like this at that point, right? That's that whole loop there. Okay, imagine I drew a nice circle there. Okay, now what about this one going into the page? So this current, I put my thumb into the page, and now my fingers curl in the clockwise direction as I'm looking at it. So I'm looking at my fingers, they like curl, oh, it's clockwise around here. Okay, and so clockwise means it's going to go up, and it's going to be pointing straight to the right at this point, because that's what the circle would look like, right? Because it's got to be a circular path, right? Like, so this is B2. This is B1. So now we have vectors that are very different directions, right? And we got to add up the total magnetic field. Okay, so let's define some things. Let's call this, say, theta. So the angle with the horizontal is theta. So that means this angle here is also theta, right? Because it's like, you know, it's geometry in alternate interior. Oh, actually, sorry, not that angle. This angle here is theta. Let's see, with respect to the horizontal, like this angle here is theta, and our B1 is like perpendicular to that. It makes 90 degrees. So the B1 looks like this. So if we want to decompose it into, say, a triangle, it looks like this and this, then this makes a right angle. So this is 90 minus theta. So this angle here is theta. So then this one is going to be B1 cosine theta. This one here is going to be B1 sine theta. Okay, so just look at the theta here, alternate interior angles, and so then this side here is the theta, because this side here is going to be 90 minus theta, and then this is 90 minus that, because right triangle. Okay, so then if we look at the net force, right, in the x direction, or not net force, net magnetic field, we have B2 pointing to the right. We'll say right is the positive direction. B2 pointing to the right, and B1 sine theta pointing to the left. And then the y direction, all we have is just B1 cosine theta. Okay? So that's going to be the total magnetic field. Now, how do we find each of those ones? The B1 is going to be mu naught I divided by 2 pi times the distance between there to there, which is A. And B2 is going to be mu naught I divided by 2 pi, the distance from there to there, which is B. And so then we have this expression B2, which is mu naught I over 2 pi B minus mu naught I over 2 pi a sine theta. Now, we didn't actually define sine theta. Sine theta is just, I just made a theta to do it. But I know sine of theta is opposite over hypotenuse, right, on this right triangle. So sine theta we know is b over a, right? So we can make that b over a. So this is going to be mu naught I over 2 pi b minus mu naught I over 2 pi a times b over a. And then in the y component, we're going to have mu naught I over 2 pi a. Okay, and then this is the x component, this is the y component. If we want to find the total strength of the magnetic field, the magnitude of that magnetic field, we're going to do the square root of the x component squared plus the y component squared, right? That's how we find the magnitude of vectors. So then, I don't know, like you can, like, I'm not going to simplify it. You can simplify it if you want, but that's basically, it's not necessary. It's just a math exercise to simplify that. That squared plus mu naught I over 2 pi a quantity squared like that. Oh, sorry, this was the cosine theta. Sorry, I didn't do the cosine theta part. The cosine theta is adjacent over hypotenuse. This is by Pythagorean theorem, square root of a squared minus b squared. So the cosine theta, we can do square root of a squared minus b squared over a. So let me make some room over here. We just got to include that cosine term there. Square root of a squared minus b squared over a, quantity squared. Like I said, you could do some math to simplify that, but the most important is that you understand we still add them up like vectors, and we still do kind of the same things. like we do with normal vectors. It's just we got to use that right-hand rule and the magnitude equation to calculate the total magnetic field. If you found this video helpful, come check out our school community. It's got an amazing bunch of features. It's got extra videos, corrected videos, better than the ones that I have errors on YouTube. It's got multiple choice free response questions. I hold live Q&A sessions and go through more problems and I answer students' questions, help with schoolwork, all kinds of things. If you want to check it out, look in the description below or check out the website and find us in the school community. You get a 7-day free trial to give it a shot, just to check it out, see what it's like, come join some calls, and honestly, come learn AP Physics 1 even faster with us.